In this video, I'll focus on how to solve circle geometry questions. I've just picked a circle geometry question from a past HSC paper. So it's on the 2005 HSC and it's question 5. So two chords of a circle, A, B, and C, D, intersect at E. The perpendicular to AB at A and CD at D intersects at P. The line PE meets BC at Q as shown in the diagram below. So all the given information is already drawn out for you. So part 1 is explain why D, P, A, and E is a cyclic quad. So before we begin, let's think about cyclic quad properties. Okay, so cyclic quads properties. So one of the properties they have are the interior opposite angles are supplementary. So that means, so these are the two interior opposite angles. They're opposite each other. They're supplementary, so they add up to 180. And another property is if I extend one of the sides in our cyclic quad, the exterior angle, so the angle on the outside, is equal to the interior angle. So in this case, A equals to B. So we should look at our quad right here, our quad, and we're going to prove they're a cyclic quad to see if they have any of those properties. So you can actually see that angle PDE is equal to 90 degrees. I'll rub out my scribbles so that you can see it more clearly. So you can see that PDE is 90 degrees and the other one, PAE, is also 90 degrees. If you're looking at these two sides, I'll draw all the quads again. So I'm going to try and do it neatly so it doesn't sort of overlap any important information. We can see that this angle and this angle are opposite. So if we add, so if we add PDE with PAE, so that's 90 plus 90 gives you 180. We can actually say that these two angles are supplementary. Therefore, PDE and rub it out, PAE are supplementary. So because we've shown that our two opposite angles are supplementary, that should be a Y, that should be a U, not a Y. Therefore, we can say that DPAE is a cyclic quad as the opposite angles are supplementary. Okay, so moving on to the next question. So I actually copied and pasted the diagram again so that we can draw on our diagrams. So the second question is prove that angle APE, so APE is this angle here, is equal to ABC, this angle there. So we can't do much with those two angles at the moment because they're not even part of the same circle. But if we focus on one angle at a time, we can come up with our solutions. So let's look at angle APE. So let's just look at this angle. This angle is part of the cyclic quad. Okay, I can't draw, it's a really wonky circle, but this angle is part of the cyclic quad DPAE from part 1. So we've proved that in part 1. So because that's a cyclic quad, D, P, A, and E touch the circumference of that circle. So if I outline the butterfly shape, see the butterfly shape that these angles make, we can say that angle A PE is equal to this angle right here, so ADE. And we can't say butterfly, so that's not the technical proof. The technical proof is angles standing on the same arc are equal. So angles standing on same arc. So the arc that they're both standing on is AE, are equal. Okay, so now what we've done is we've actually identified an angle that's inside the original circle. So if I outline the original circle, so that's our original circle here. I'm going to rub out all this part so it doesn't confuse you. So I've just got the original circle. You can notice that angle ADE makes a butterfly shape with ABC. So therefore these two angles are equal. So we could say that ADE is equal to angle ABC. Makes a butterfly shape and they're standing on the same arc, which is AC. So it's the same rules. Angles standing on the same arc, and the arc is AC, are equal. Okay, so now by default, if ADE equals to APE, we can substitute these two angles. So therefore, angle APE is equal to angle ABC. So that's the second question done. So first question done, the second question done. Moving on to the third question. So the third question is, hence show that PQ is perpendicular to BC. So when a line is perpendicular to another line, it makes a right angle degree. So I'm going to put a right angle there. If you're just looking at the diagram, I'm going to try and highlight something that's really useful for us. So I'm going to highlight two angles. And you can see that the angles I've highlighted actually make a butterfly shape. So if we can prove that these two angles, PQ is perpendicular to BC, if I can prove that this angle here, so PQB is equal to PAE. So to do that, only angles that are lying on the circumference can make that butterfly shape. So that's telling us that we need to sort of show that the angle PAQ and B are cyclic. So we need to show these all lie on a circle, the circumference of a circle, so they are indeed cyclic. So from part 2, we know that angle APE is equal to angle ABC. So if we've shown that these two angles are equal, therefore we've actually shown that APBQ is a cyclic quad, as angles standing on the same arc are equal. So because these two are equal, we can say that they're both standing on the arc AQ. So our arc is AQ, therefore all these 4 points form part of the circumference of a large circle. And A, P, B, and Q are cyclic quads. So they're cyclic quads, then we can see that the other angles, the bottom angles of our butterfly wings, which is angle PAE and angle PQB are equal. And that's the same reason. So the same reason, angles standing on the same arc are equal. So the arc that they're both standing on is PB, that big one there. PB are equal. So because these two angles are equal, and we already know that PAE is 90 degrees, therefore we can also say PBQ is also 90 degrees. Therefore, I've just shown that angle PQ bisects BC, because I've shown that PQB is 90 degrees. So that's how you do the final question.